Hi, this is the next in a my series of videos on SCAD-DTS, and up until now the focus has been on the thermohydraulic circuits, whether they be single phase air, pneumatic, or two-phase flow. But one of the things that is useful and basic requirement is the ability to control devices within the circuit. And in this particular case, I've expanded the features on SCAD-DTS to include wiring diagrams. The means of transferring information between circuits in an object-oriented design can be done in different ways, but in this particular case I've chosen to use a publish and subscribe mechanism that enables the easy application of solenoid coils, transferring that information to switches, and from say pressure transmitters to switches as well. And you'll see that within the circuits that I've set up for a multiport valve, the control of pistons. And this becomes interesting because from that perspective the system can be used in order to validate wiring diagrams or PLC ladder logic. Doesn't focus on transferring that information through to a PLC. I don't have that ability, but the ladder logic itself can be validated, and that's a significant aspect of any PLC ladder logic. So what I'll do is I'll go through the circuit, and we'll see how that's obtained. So first of all, we'll log in and sign in to the account, and then I've created a Multiport Valve project. Within that project I've got two systems, but we'll take the lower one, and within that system we have these two circuits which are related to each other. This is the wiring diagram circuit, and as you can see, the engine that's being used is the electric single phase. And then we have the thermohydraulic circuit, which is in the subcooled engine, using the subcooled engine, and we'll see that. So what we'll do is select the wiring diagram, and it comes up with the wiring diagram circuit, and then we'll go to the control and just start the circuit, and then we'll go to the thermohydraulic aspect of it and go to the control and start that circuit. So if we go to the states, we can see that both those circuits are running. And if we go to the page, and just to validate that, we'll have a look at the pistons, and piston 1, which is here, and you can see piston moving, and piston 2, which is here. Okay, so with the two, with the way the system is set up, what I'll do first is bring up the Multiport Valve window, and we can see the solenoids changing state, and then okay, so we got solenoid A here. There's only one solenoid associated with this device. whilst there's two solenoids associated with this particular device. The state of the solenoids is determined by the wiring diagram, and we'll go into that in a bit, but we'll focus on this particular drawing first. So if we go to, let's say, node 2, which is here, and we can see that the pressure is 618 psi, that's absolute, and that's being controlled by the upstream pressure regulating valve, PRV1, and that's controlling the pressure, so recirculating the flow back into the tank. And the no load pressure on this pump is around about 1,000 psi. Whilst the fluid is, if the solenoids were de-energized, then the flow would just go through this line here and back through to the tank. And node 1 is considered to be the tank at ambient pressure. Okay. When the solenoid, in this case, it's now changed. Solenoid A is energized, then the flow is through, so that this line, which is link 3, corresponds to this position here, and link 4 corresponds to this position here. And in the case of solenoid B being energized, which is the case now, then there's a cross transfer. And we can see that if I look at, let's say, node 3, you can see it's 618, and node 4 is 14.7. And of course, as the solenoids change state, then the pressures will transfer accordingly. And that's what's just happened, 618, and now this is 14.7 as the solenoids change state. And that corresponds to the piston moving in the appropriate direction. And the same thing applies here with the solenoid, the single solenoid. When it's energized, then this moves across, and then the flow is through. Otherwise, it's cross flow. And the way I've set it up is, you may know the convention already, but the convention is open and closed chevron corresponds to the link index, and when it's not open and closed chevron, then it's a node index. And that's essentially it, except for the fact that the multiport valve has its own index, and we can see that if we go to the control diagram, and if we have a look at the multiport valves for this particular circuit, then we can see that the multiport valve number 1 has a single solenoid, and multiport valve number 2 has solenoid A and solenoid B, and that will change state in the same way. The links correspond to the internal. These are the external indices associated with the link, and then the internal nomenclature is given by A, B, C, D, E, F, G, and H. If we go back to the circuit, then we can see that nomenclature corresponds to the A, B, C, D, and E. E is across, and F and G are diagonal. Okay, so let's have a look at the wiring diagram. So if we go to the circuits, we are at the circuits here. So go to the wiring diagram, and this becomes interesting. Well, what we have is several switches. And these are the proximity switches, PX1, PX2. And then we have an internal relay switch, which is normally open. The solenoids for device 1 is solenoid A and B, and for device 2 this is solenoid A. There's only one solenoid. And then we have the position switches LS1 and LS2, A and B. LS2 is high, the high side, and this is normally closed whilst this is normally open. In the case of the proximity switch, this is the low side and it's normally closed, and this is the high side, normally open. Then we have the pressure switch, which comes from, if we go back to the thermohydraulic circuit. Okay, so the pressure switch is here, and so it closes when the pressure exceeds 500 psi. And then you have the proximity switches PX1, PX2 on piston 2, and the switch, mechanical switch, LS2 and LS1 on this is piston 1. So we go back to the wiring diagram. Now the wiring diagram is solved using an electrical solution. In other words, using Kirchhoff law. And so if we look at the voltage on, say, node 1, and we can see that it's 20 volts. Now, it's a bit tricky, sort of, everything is dynamically being computed, but we'll go through some of the results here. If we look at the link on 3, and we can see that solenoid A is de-energized, and if we look at solenoid B, which is on 7, that's de-energized. Okay, so that's changed state. It's now energized, and this is de-energized. And we can have a look at the proximity switches. So link 1. Okay, so that switch is open. There's no current allowed through whilst V is equal to 0. And if we look at 2, that's also just changed state. So now it's open. We got current through. Not much current, but this is a logic circuit, so a wiring diagram, so it's expected. If we look at link 4, it's energized, and link 5 is there, link 6 is there, so that's open. Link 8 link 9 and link 10. Yeah. Yes, that's right, link 10. Link 11. Oops. 11. And link 12. 13. And 14. And 15. Okay, so that's all the links. You wouldn't look at everything in the same way as I'm doing in this example, but it really shows you the dynamics of the system. And so in this particular case, all right, so what we have is a switch. If I change the state of the switch, and you can do that by selecting V, which is the switch, and since this is a manual switch, I can change the state. Then this path is down, but because this switch is closed and this switch is closed, so we have current that runs through to energize this relay. But as this relay opens up, then we lose power to this relay. This is the relay switch. As that switch opens up, then we lose power to this relay, and that becomes de-energized, and it stays de-energized. So, and things, I think, become pretty stable because solenoid A is de-energized, solenoid B is de-energized, and so and then solenoid 2, or solenoid A rather, on device 2 is de-energized. And so if we go back to the circuit, oops, I'll go back to the thermohydraulic circuit, then we can see that those two solenoids are de-energized, and in that state we just have recirculation back. PS1 is, if we look at the, say, the node, well, we got it here, it's 19.7, and this is 438. So in actual fact, the piston is fully extracted in its high position, and this one is in its low position. If we look at say node 5, it's 14.7, and node 6, 19.7. So yeah, there has to be a pressure differential of around about 20 psi for it to actually move. So it's stuck in this position at 0.17, and as I say, all the pressure is recirculated back into the tank. Now if we go back to the circuit again, the electrical circuit, oops. And as I say, we can see that everything is back in the static state. If I close the switch, oops, okay, so then becomes energized, and then solenoid A becomes energized, solenoid B is de-energized. And if we go back to the, so we can see it here. So the solenoids have changed state. So all this is being computed from the wiring diagrams and overrides the solenoid positions in the thermohydraulic circuit. Now, the way in which this is done is, if you go to, say, the, let's go to the control and let's have a look at the MPVs. So you'll see that for solenoid A, what we have is a subscribe key, and for solenoid A and B, in the case of the two solenoid, then we got two keys. These define certain information that enables the transfer of information from the solenoid valve being computed in the wiring diagram to the thermohydraulic circuit. And if we go to the wiring diagram, because this is the thermohydraulic circuit, if you go to the wiring diagram, and if we go to, say, let's go to link 3, and if we go to go to link 3. Link 3 is the coil, and it's the coil for solenoid A. So if we go to the coil, and we can see that there's a publish key. That publish key is copied and transferred to the subscribe key, and using that information, then I can compute the transfer of information from the coil to the switch, and by that means complete the loop between the two circuit diagrams. So it uses a publish and subscribe mechanism, and becomes very effective and very quick in being able to set up the design. So that's about it. There's, as you can imagine, you can go into a great deal of detail on these diagrams, and this is a relatively small circuit, but it does show you that there's a lot of detail that goes into it. And apart from looking at the change in state, you can also make plots. So yeah, you can add a plot, and if you go to the plots, then you can, that was the field that I've just added, and these are fields that I've added previously. So you can say start the plot. Okay, so you can start the plot. Now I've got the 3 plots set up here, and there's various features that are available within the plotting software. One of which is being able to adjust the maximum minimum value, and so you can focus on different elements within the plotted variable that might have different ranges, and so you can do an analysis accordingly. Okay, well, thank you for listening, and I'll be putting this on YouTube, and you'll be able to access it through a reference and in the emails that are sent through. Okay, thank you very much.